Okay, thank you, Mr. Chairman. So we are switching to metal. So the toughness in that case will be multiplied by about 100. Be careful. So we're still studying a nuclear pressure vessel steel, this one. And we are interested in the ductile to brittle transition. And in this talk, I'm going to speak about the lower parts, so the brittle behavior of the material. The ductile behavior of the same material was presented at the beginning of the week by Emmanuelle Catel. So the context is the nuclear pressure vessels in France. We have a lot of pressure vessels, you know. They are aging, and we want to be sure that they are still safe. And they can be affected by thermal aging, by irradiation, and so on. So we want to develop experimental method, but also analysis method to guarantee that this structure remains safe and that we have a sufficient safety margins. As I said, I will stick to the brittle behavior here. So I will speak about the material, the mechanical test, the elastoplastic behavior, which is very important to analyze what is going on in the cracked specimen we are using. Some few words about the simulation tools and the simulation tricks we're using, and we will apply that using the very standard, very basic very mean model. So here's our material. That's a very modern one with a very low sulfur content. Here in this picture, you can see manganese sulfides inclusions as well as titanium nitrides. We selected this picture because on the single image, we can see both, but actually the volume fraction of these inclusions is very, very low. And if you take random pictures, in most of the cases, you see nothing. So this is more of an exception than something else. And we have been using tests between -150 and -20 C. So we had tensile tests, regular smooth bar on different notch bars with different notch radii from 20 microns down to 2 microns. And this increases the notch severity and the stress reactivity within the material. We also use a cracked specimen. So most of the time we use CT specimen with different sizes to check for the size effect. So we have 12.5, 25 and 50 millimeter. That's a fairly big one, a heavy one. And W is the width here of the specimen. And at the same time, we also use SCNT, single edge notched specimen, only one geometry, which is given here. And the interest of these two sets of specimens is that we develop different stress states. And I will show you that later. So first, some mechanical test results. So when you do a tensile test, for instance, on a notch bar, here what you have is the relative variation of the minimum diameter, and that's here the normalized load. So as you know, as we decrease the temperature, more or less, the material becomes much harder. If we collapse all this, we can collapse all these curves by dividing the normalized load by this reference sigma y stress, which is the average of the yield stress on the UTS, the ultimate tensile stress. If you do that, we only get one curve that will be very helpful to derive a hardening of its material. So that's a fairly busy plot where we gather all our experiments. We have about 150 tests, so that's a lot. So here you have the three test temperature. Each symbol, just you have a shape and a color, represent a different specimen. And here, for instance, at -150, we are here the CT25, CT 12.5, and here the SCNT. When the symbols are open, that means we have purely brittle fracture. When the symbols are full, that means we get a little bit of ductile tearing before cleavage. And in this presentation, I'm not going to analyze those points. Okay, so I will only stick to the open symbols, but we still have many of them, and that's okay. And we compute the toughness from the J value based on Irwin's relationship. And J, in that case, in the case of the CT specimen, is calculated using the ASTM 1820. And in the case of the SCNT, we are using FE simulation to compute the J values for each specimen. Okay, here we must also have a look a little bit at the fractographic surfaces. So here that's very low temperature, fully brittle. So you see the pre-fatigue crack here, and here that's fully brittle. Toughness is 32. Here we go to the SCNT specimen at -100. So you still have the fatigue zone. The stretch zone, that's the fact that the crack tip is actually blunting due to plasticity. And a little bit of shearing here that we do not consider. And here you have a fully brittle fracture. Toughness here is 175. And we go to -50. So we get the fatigue, stretch zone, shear zone. Ductility, you see a little bit large dimples here. And here at the very top, it becomes fully brittle. So this kind of specimen, we don't analyze them here because there is a little bit of ductile shearing. Okay. So we need, as I said, an elastoplastic behavior. So we are going to express it as the product of this sigma y reference stress, which is tabulated from the test, times a function of the accumulated plastic strain, epsilon p, which is temperature independent. On here, you have some example on how good or how bad the simulation is for different temperatures on different geometries. I think the thick is okay. So with that, we can go and simulate our specimens. We are modeling only ductile failure. So it's sufficient to have elastoplastic behavior, no ductile damage. So it's not so difficult. A very important point is that we are using finite strains. Because even if the specimen remains elastic, at the crack tip, there is a blunting, which affects the stress field. So even if the macroscopic behavior is purely linear, at the crack tip, you need to account for finite strains. And we have to adapt the mesh size relatively to the fracture process zone, which is about the ratio of the J value you want to reach divided by this sigma y stress. So we use a mesh size which is indeed much smaller than this ratio. Okay, and another problem is that when you have very high plastic strain, you may have fluctuation of the pressure. So we use specific elements which are called mixed elements, where we have the displacement, which is interpolated with this quadratic shape function, and the pressure and the volume variation, which are interpolated using linear shape function. So I mean, the extra computational cost is very limited because you have something that is quadratic for the displacement and linear for the other variables. So it doesn't cost so much, and it really improves the quality of your results. So here are some examples of the stress field at the crack tip. Actually, that's the pressure here. That's the standard bilinear elements. We know it's very poor. So it's just to show you how poor it can be. Usually the people used an F-bar method to get rid of this checkboard effect. And this gives a very nice distribution of the pressure. We don't use that because the next step is to go into the simulation of ductile failure. And in that case, we also need this kind of mixed element with quadratic and linear shape functions. So we have to use quadratic interpolation for displacement. So that's what you get with a full integration. Reduced integration improves a little bit the result, but not so much. But if you use this mixed element, you see that these checkboarding effects almost completely disappear, and we can end up with a stress field that we can work with. So then we have done our elastoplastic analysis of the test. So we need to have some kind of brittle failure criteria. So we're using the very original, very mean model. So we define an effective stress, which is the maximum over the load history of the principal stress, assuming that plasticity is active. And the Weber stress is defined by this integral, where the parameter m is an unknown that you need to fit, and which basically represents scatter. And then you make this. You take this integral and compute the failure probability by introducing this sigma u, which basically represent the failure stress at a given temperature. Okay, and we started to do the test at -100. Why? Because that's the temperature for which we have the more specimen. So on this at this temperature, we fitted both M and sigma u. Okay, so here what you have is the probability of failure as a function of the Weibull stress for all specimens. So we used all specimens to do the fit. So you see that the fit is okay. So we have an M of 18. Okay, I don't know. 8 of 18. What is okay on this curve is that you have all, you know, on the curve here, all specimens are more or less evenly distributed. We don't have all the CT50 at the bottom and all the SCNT at the top, for instance. That would be a very bad fit. We can check that by plotting the fracture toughness, the measured fracture toughness probability, and you see that we have a fairly good representation for all geometries. So the first three curves here are for the CT, and we see clearly a size effect. These are the big CT, and that's the small CT. And this one here is for the SCNT, and we see that the stress state in the SCNT is beneficial, and you can get higher toughnesses. So we did the same exercise at -150 and -50. We keep the same parameter M and adjusted the sigma u parameter. The fit is more or less okay. At -50, you see, for instance, here for the SCNT specimen, with there's a large dotted part here because that's the region where we have ductile failure. So we just can analyze one point, which is purely brittle. And the fit is very good here. Okay, 1 point. But I mean, everything is fitted on the other points also. And so what we get is that sigma u is an increasing function of the temperature, which is something we found a long time ago on other teams also, with a less refined analysis of the stresses, and we confirm very much this trend, which is important for us. I think I'm running out of time, so I want to outline the importance of using the SCNT. Adding the SCNT was very helpful to get a good fit. And the reason why is that the stress field ahead the crack tip, you see here, you have a bump here because of plasticity. And if for the three CT specimen, that's all the same. Basically, the stress state is the same, and it's different with the SCNT, and that gives you more data point, a relevant data point to make a good fit of your parameters. So I will conclude just here. And obviously, the next step is to mix the ductile behavior we have described at the beginning of this week with this brittle approach. I didn't have time to go into the very details of the numerical recipe we use. Just pointing out that we are organizing a TC8 ASIS committee meeting about numerical method for fracture. It's going to be next March. So if you are interested, just contact me. Thank you.